All right, today's notes are going to be on water phenomena. What we're going to be looking at here are the waves, tides, but we're going to start first with a little bit of information on some special events. And that special event is what we call the El Nino Southern Oscillation, also known as ENSO, E-N-S-O, or for short, we just typically call it El Nino. El Nino is because there's a buildup of warm water occurring in the central and eastern equatorial Pacific that is along the equator in the Pacific Ocean, an area that normally on this side towards the Americas does not have a lot of warm water. Here's the normal condition. And in that normal condition, the trade winds, remember trade winds are very important, are blowing in both the southern hemisphere and in the northern hemisphere. And they're pushing this warm water along the equator in this direction. That's part of that ocean conveyor belt system. And most of that water does pass through Indonesia, but a lot of it will pile up over here, so we have a whole bunch of warm water. Since the water's been pushed over here, it allows for a tremendous amount of upwelling off the coast of South America. A lot of cold water coming to the surface there. This is our normal condition. When we have an El Nino, this water moves back across the ocean. So those are the normal conditions. Now, how does this particular process begin? Well, the first thing that has to happen is we have to have those winds that are pushing this water over here get weaker. And so the winds will slack, or in some cases, in some years, they actually will reverse for a few weeks. Not an extraordinarily long period of time, just a few weeks. When they relax or when they reverse, the pressure on the water is not there any longer. This mound of water that's over here flows back down slope. And so what you can see here in this cross section, so over here on the right is the normal condition. We have these trade winds pushing this water over here, allowing that cool water by South America, that's represented over on that far side, to come up to the surface. Well, when these weaker trade winds relax, that warm water pushes over, and that's a little bit of a problem, because now we don't have all these nutrients coming up to the surface. Huge issues for the organisms living on this side of the Pacific Ocean, closer towards South America. This happens about every 2 to 8 years before those trade winds become stronger again and are able to push that water off to the side. That's the big change, the trade winds and this area of warm water. So make sure you go back through that reading and understand what is exactly happening when the El Nino Southern Oscillation and ENSO event actually is occurring. Sometimes after El Nino ends, and here's some satellite imagery of El Nino in 1997. You can see the warm water. Here's the United States. This white area is the warm water that's pushed across the ocean to where it normally isn't. What can happen when these trade winds increase again is sometimes it gets a little bit stronger. And when we have those really strong El Ninos, really powerful ones, lots of water, we get this overcorrection. And that overcorrection is called a La Nina. It's the opposite. And what happens here is that we have a huge area of upwelling, has extraordinary changes to the climate in the southern Pacific Ocean, especially around those islands in the South Pacific and off the coast of South America. La Nina is a cooler than normal condition. The next thing we're going to be talking about is tides and how these particular tides form. One of the things that you really need to understand about these tides is that they're formed because of the gravitational pull that the moon and the gravitational pull that the sun have on the earth. Now, remember, water is not actually attached to the earth, it's on it. Okay? So when the sun and the moon have this gravitational pull, they're pulling things that are on the earth. In this picture over here in the upper right, we have the moon up here, and we have the earth over here. A little bit harder to see just because of the coloring, But what happens is the moon is going to pull the water that's closer towards it, closer to it. And so we get this bulge of water on that side where the moon is. The other side of the Earth over here, the water is not being pulled, and so it kind of relaxes and slacks back a little bit, so we get another, much smaller, but there is another bulge here on that other side of the Earth. Now, the sun also helps to have an effect on these bulges. So it matters greatly where the moon and the sun happen to be. Now, as we have this bulge here, remember the Earth is rotating, but the moon is not rotating nearly as fast as the Earth is rotating. And so the Earth rotates, and as we have these little red people stuck on here, as these people rotate into where this bulge is going to be, the water is going to increase its height on land, and then as they rotate out of the bulge, the water is going to decrease its height on land. They'll rotate into the backside over here, away from the moon, and there's going to be another increase, and then another decrease, another increase, another decrease, etc. Now, how does the sun and the moon actually play a role together? How are they working together? Well, they form a couple different types of tides. The first type of tide is this one here. It's called a spring tide. And a spring tide that we'll talk about are the tides down here. Now, a couple things you have to understand very quickly about the sun and the moon is those phases of the moon. We have full moons, we have quarter moons, we have new moons. When it's a full moon, that means the Earth is actually between the moon and the sun. So the sun's rays shine, hit this face here of the moon, and then we see that full reflection of the sun's light off of the moon. When it's a new moon, that means the moon is between the sun and the Earth. And so the sun's light hits the far side here of the moon and reflects away from us, so we do not see that full reflection of the moon. In both that full moon and what we call the new moon, where we can't actually see the moon very well, the sun and the moon are working together. So we have the highest high tides and the lowest low tides when we have the spring tide. It's our largest tidal range. So spring tides, the moon and the sun work together to get a huge bulge. And here, the moon and the sun, you might think, but they're working opposite each other. But remember, here on the side closest to the moon's going to be affecting those tides greatly. The side opposite the moon, it's going to be relaxed. It's going to be falling away a little bit anyway. So with the sun being on that same side opposite the moon, it pulls that water even more. So we get a combination effect here. And of course, when the moon and the sun are on the same side, they're going to be pulling together. Highest highs, lowest lows for our spring tides. The second type of tide is called the neap tide. This one has our smallest tidal range. That means the difference between the highs and low tides is the smallest. And that's when we have the quarter moon. So the moon and the sun and the Earth form a right angle. And this moon could be down on the other side also and forming a right angle. Either way, depending on the month. Our neap tides have our, and this is kind of confusing, lowest high tide. So the water doesn't get very high up the beach. And then it has our highest low tide. That means the water doesn't go down very far because the moon's pulling it a little bit this way, the sun's pulling it a little bit this way. We don't have these huge increases at all. That's our smallest tidal range, is what we call the neap tides. Now, we do have some different patterns and different currents because of these particular tides. It's a little difficult to see these, but looking at the graphs is the important part. I'll kind of point these out for you. Our diurnal tides, that's this graph over here on the far right. This is where we have one single high tide and one single low tide, so two tides in a day. And you look at this graph and go, but wait, there's only a high tide. Yeah, but here's half of a low tide and half of a low tide. Depending on the day, sometimes these tides are right around midnight. So it will split between 2 days. But we have this one single high and one single low tide. The next one is a semi-diurnal tide, and that's the one over here on the far left. That semi-diurnal, that means we have 2 high and 2 low tides that are about equal. each and every single day. And then we have the mixed tides, and these are the ones actually along our coastline, these mixed tides, excuse me, where we have 2 high tides and 1, 2 low tides every day, but the high tides are not the same. There's a higher high tide and a lower high tide. Same with the low tides. There's a higher low tide and a lower low tide on every single day. So we have these unequal high and low tides each day. Now, as the water's moving in and as the water's moving out, it forms currents. And we have these particular kinds of tidal currents. When the water is coming in, think of it as flooding the beach. We call that a flood current. That's the inflow current. When the water is coming out, leaving, it's a slack or ebb current. You'll see both of these particular terms when we talk about tidal currents. That's when the water is flowing away. It's going to that low tide. And then there is a point that's going to be in between these, where the water isn't moving in one direction or the other, and that's called the slack tide. It's the midpoint between that high and low tide, where we don't have a lot of water moving in any particular direction. Now, this information is really important, or it has been for people, since we started sailing and utilizing the oceans. Because if you think about a bay like this one, well, this is where we have docks and ships coming in, and this is where people are living. How do we get the ships to get out into the ocean? We can't just wait for the wind to blow, because there will be weeks where the wind is blowing inland. I mean, there's plenty of movies, Pirates of the Caribbean, where all of a sudden the ships are just going out to sea. Well, they go out to sea because they're on these ebb currents. So they wait and measure when these tides are going to happen. And when those tides are going to happen, they make sure that the ship's loaded up, everybody's on, they untie the ships, and the ebb current is going to take these ships out to the ocean, where then they can rely on the winds, which are much more constant when you're way out at sea. The parts of the wave that we have, a couple different things that we should know about the parts of the wave, not a tremendous amount. Number 1 is the crest of the wave, and the crest of the wave is located up here at the top of the wave, so don't think too hard about where the crest would be. That's our highest point above sea level. The trough of the wave is down here on the lowest point of that average sea level. And this dotted line that you can see here in this particular picture, that's showing where the average sea level is. So we have a crest up here and then a trough down there. Now, once we take a look at how high this crest is and how low the trough is, then we can see what the height of the wave actually is. And that's this measurement from the crest to the trough, the vertical distance. Now, if we take a look at from crest to crest or from trough to trough, that's going to be the length of the wave. So the wavelength is that measurement horizontally from identical points on 2 waves. Typically, we go crest to crest or trough to trough. That's an easy point to find. The period has to do with time. It's the time it takes for the same spot, so for this crest and this crest, to pass a particular point. Oftentimes there's buoys that are out a ways in the ocean, and that's what we're actually measuring, is how long it takes for a crest to move that buoy up and another crest to move that buoy up. That's the period of the waves. And then frequency is our final one, and frequency is how the number of waves that can pass, say, that buoy or a particular point in a certain amount of time. Now, the period and the frequency are pretty useful ones, especially if you're in the water. You know how long you have between waves, and you know how often these waves are going to be appearing. So if you're surfing, kind of have an idea as to how fast you need to get back on your board and start paddling before that next wave is coming in. So these 6 parts of the wave, not essential, but there will be questions on the test on those particular parts of the wave. Now, how do we get waves in the first place? Well, there's something that has to disturb the water. So we have what we call disturbing forces. And don't think too hard about what those things happen to be. Disturbing forces, the wind is the most important one. It's the most common. We've talked a lot about wind and creating these currents. Well, they're creating these waves. That's part of those surface currents. The wind does that by friction. We have changes in the gravitational pull. I just talked about those tides. Those are going to be causing waves, so that change in gravity. And then the last one here is seismic activity. When there's an earthquake and the ocean bottom actually moves, pushes water, this is what causes tsunamis, a very particular type of wave. Now, when we combine these things together, or we utilize this wind, it's going to create a maximum size of waves. And there's a few things that we need to get those really big waves that people like to surf on. But we need wind speed. That wind needs to be blowing very, very fast. The faster it's blowing, the more water it's going to push, the larger the wave. That wind needs to be blowing really, really fast for a particular duration, a long period of time. And then we need also what we call the fetch, a fancy word for a big space. Wind needs to blow really fast for a long period of time over a huge area. Think of it this way. Go to Folsom Lake. The wind could be blowing at 50 miles an hour for 2 weeks straight, and we're never going to get a very big wave. Or big waves, plural. Because it's not a very big area. Small, what we call fetch. Pacific Ocean, huge area. The wind could be blowing very, very fast for a long period of time over a very big area, and we can get enormous waves off of the coast of Half Moon Bay, just south of San Francisco. We have huge waves forming because the wind is blowing very fast for a long period of time all the way across the Pacific and hitting that particular area. Now, when these waves are coming into shore, one of the things that we kind of worry about a little bit when we're interacting with these waves is what's going to happen when they crash over the top. Well, there's a reason that they crash. And they crash because it's the actual bottom of the ocean that's going to affect them. We don't have waves crashing far out to sea because it's too deep. But when they get closer and closer and closer to shore, that's when these waves start crashing over the top. And they start crashing over the top because as the waves are moving with a pretty constant wavelength, pretty specific speed, they start to hit the bottom, and the bottom slows down the waves. As it slows down, it compacts that energy together. The waves have to have that energy go somewhere, and so the waves actually increase in height. When that height reaches a particular ratio with the length, that ratio happens to be a 1/7 ratio. When it reaches that 1/7 ratio, that's when it starts to crash over the top. Now there's 3 different types of crashing waves, or what we call breakers. Excuse me. First one up at the top here is a surging breaker. Don't think too hard. Again, when it's surging, it's coming in very quickly. It hits a very steep beach slope, so it has a very short area to slow down, and it shoots it up really high and crashes down with extreme force. Again, Half Moon Bay. There's a reef out a couple hundred meters. When those waves that have been pushed for miles and miles and miles and miles across that Pacific Ocean hit that reef very quickly, they shoot up to 50, 60, 70 plus feet in the air and crash down with extreme force. Those are the surging breakers. That's where they have a competition called Mavericks. Plunging breakers, the next one here, these moderately sloped beach. Areas like the North Beach of Hawaii where there's some pretty big waves. These are plunging breakers, moderate slope, so it slows down relatively quickly, but it still has a little bit of distance where it can start that slowing process. Gets those good tunnels that so pictures of surfers inside the tunnels. That's the plunging breaker. And then the last one is the one that actually most of us are familiar with. Those are called spilling breakers, the gentle beach slope. This is the area where most of us go to the ocean. We go to the beach. It's a nice, wide, flat beach, and you can walk out a little ways. The waves are not big, maybe 3-4 feet high. And when it crashes over, it just kind of spills over the top, not this huge tubular crashing. Those are called the spilling breakers. Very slow deceleration, and it's a slow process to get to that 1:7 ratio. That's all for the notes on tides. Make sure you understand the process of how those tides form, the spring and neap, where the sun and the moon are. Make sure you understand how those maximum wave sizes are created, how those waves actually are crashing onto the shore. And then, of course, make sure you go back and understand the information on an ENSO event, El Nino Southern Oscillation. Look forward to seeing you in class next time.